And hello everybody. I'm not at all prepared for this. Okay, so before we get into the chaos, I acknowledge the traditional owners of this land. I pay my respects to their elders, past and present, and to Aboriginal elders and peoples from other communities who may be taking part in this live stream today. So, first thing to check is... audio. I think we have audio. I can see the levels. We have Astro, we have Andy, we have Steve, we have Evil Steve somewhere there. And yeah, Steve is running wild. So it's been we're trying to juggle things at the moment because this is the first time I've done a live stream, I think, with someone else, apart from when we were doing the Open Hardware Miniconf, where we've had a couple of us here and we needed to be able to capture different things, so it's a bit of a complicated arrangement. So, where to begin? Alright, first, I hope you're having a fantastic weekend. This is my friend Andy, who many of you will already know, and who is regularly in the chat in the live streams. So you've probably interacted with Andy many times, maybe not seen his face before, and now you can just see the little strip of eyes. So the backstory to all of this is that Andy and I have been collaborating for many, many years now on first the Arduino Miniconf, and then that kind of morphed into the Open Hardware Miniconf once we broadened it beyond the scope of just Arduino. And how long have we been doing that? 13 years?
It's the 13th.
13 years. This is our 13th year coming up every year, collaborating on doing this little hardware conference. And so over the way the conference runs typically is that we have some kind of a hardware project that we focus on, and then we have talks on other subjects as well. So each year we think about some kind of a project to work on that we can get everybody to assemble and to and to collaborate on. So this time what we are doing is collaborating on a project which incorporates an FPGA, which I've never used before. I've got a couple of odds and ends of FPGA boards that I've supported on Kickstarter over the years and stuck them in a box and never even used them. So Andy has been doing a fair bit of FPGA stuff over the last little while, and this is my chance to try to figure out how they work. And yeah, so did you want to give any more of an intro?
Oh, so what I think is ironic is of all, I perhaps have some expertise in some areas, but John's brought me on to talk about the thing that I've only just started getting into, which I know the least of. So it's going to be the blonde leading the bald.
Yes. Oh well. Okay. We can ask you for help.
Yeah. Anyway, so what can we do? So
all right.
We've got some things to show.
Yes. So I was thinking that maybe. So Andy claims to not know much about this. I think he knows a little bit more than he claims. I know nothing about this. So I think what we're going to do is basically go through a sequence where we're going to talk about a little bit about FPGAs, what they are for, why would you care, and then through some of the history of how we've ended up using an FPGA in this particular Open Hardware Miniconf project. And we'll show you a little of the project, look at some of the tool chain and that sort of thing. So I am going to be the person asking the silly questions and not knowing what's going on. So I suppose the very first thing is the real FPGA 101 question, which is what are they and why do we care? And so from my very limited knowledge, so an FPGA, Field Programmable Gate Array, is an IC that you can reconfigure to operate in different ways. So it's like a toolkit that you can modify at an electrical level to behave differently, which is a little bit different to, say, a microcontroller, which has all of the circuitry. It's basically hard. It's not going to change. You cannot modify it other than changing flash, setting fuses, those sorts of things. You can't radically reconfigure them. Whereas with an FPGA, you can reconfigure the actual electronics within the chip and make it behave in a different way, which means you can give it different characteristics or personalities depending on what you want to do. So it allows the configuration that you normally do in software to be pushed further down the stack. Am I on track here approximately?
Yeah, certainly. Maybe we should just pull some FPGA boards out. I'll move the downward camera.
Go for it.
Okay. So often, from Kickstarter projects or off from various websites, you can get FPGA boards that look like a normal development board. So that has a lattice, I think it's an LFE F25, so an ECP FPGA. And it'll have some USB ports, some flash memory to help you boot up or program the FPGA. A slightly larger one, more popular, is this Artix A7. So it's got that's the RT-A7 board from Xilinx, or from Diligent, using a Xilinx chip. And that's got 100,000 logic cells on it, so that's a fairly big FPGA. And so these are the things you start with. And then you can get some application projects. So this is the NETV2 from Bunny Kong. And it's basically got the same Artix A7 chip on it, hiding underneath this heatsink. So that's how people typically start, and they use a vendor's toolchain. So something like they'll use Vivado from Xilinx, and these things are massive. They're like a 20 or 40 gigabyte download, and they're not open source, and they can be quite. I personally find them quite unwieldy. And I was hoping to work with things that are more open source toolchain. And so people like Tim Ansell from Google and Sean Cross for many years now have been working on and promoting open source toolchains along with a whole bunch of other people. So hopefully we can show some of that stuff today. But just to reiterate on what John was saying about an FPGA, basically what you have is the guts of it is what's called a lookup table. I'll just get this in the middle of the screen. And so a lookup table is effectively, if you have so how am I going to do this? A bunch of Boolean inputs, so basically this is a lot 4, and these can be either 0 or 1. And basically it says for each of the combinations of zeros and ones, what output do you get? So you have an output here. Is that readable? Yeah, yep. Great, cool.
Yeah. So I'm going to keep asking silly questions here to keep clarifying.
Sure.
So effectively, this would allow you to define a logic gate. Like you could say, I want a 4-input AND gate or an XOR or something.
Exactly.
By defining the logic table.
Yep. Yeah. And so basically it means if you've got 0, 0, 0, 0, if it's an AND gate, that would be just 0. If it was 1, 1, 1, 1, that would be a 1, and everything else would probably be zeros.
Yes.
And so this is what's called combinational logic, and it's called combinational logic because you can have any combination inputs and produce outputs, but it has no state.
Yeah, it's a gate.
It's effectively a gate, the chip that we're looking at from Lattice uses a LUT 4, but sometimes you can also get LUT 6, which just basically has a couple more columns there.
Mm-hmm. Okay.
And then, now the next thing you have is you can have a flip flop. So, do you want to describe what a flip-flop is?
A flip-flop is a logic gate which changes state between the output changes state based on the inputs. So, what I just said could apply to any logic gate.
Basically, it retains its state. So if if you're clocking, and you basically have input 0 out, it'll basically retain the state. Mm-hmm. And if that becomes a 1, that stays a 1.
Yeah, so that's like a latch.
Yep. And so basically you can take the output of the LUT into the flip flop, mm-hmm. and now what happens is you can as you clock, you can now retain the state from clock period to clock period, and mm-hmm. This is called sequential logic. And this together is what's is inside the FPGA becomes a logic cell.
Okay.
And one way to
just to clarify, so what that means is that this, which is effectively being a latch, is going to be allowing you to capture the output of this gate and hold it, so that if you've got multiple logic cells doing things independently, if they're all running off the same clock, it means you're going to be synchronizing the output of those gates. Is that correct?
That's right. So what you'll have is effectively what's called a global clock.
Yep.
Gosh, terrible. Can you see that?
It's just off the edge.
A global clock.
Yep.
Actually, I'll do this on the other side.
Might need another sheet of paper.
A bit of paper. You'll have like a global clock, and that'll go out to effectively a bus, which is driving thousands of these little cells.
Mm-hmm.
It just goes on like that. Now, so you can pretty much build any circuit you like, any digital circuit you like out of these cells. And so the FPGA we're looking at today, which is a lattice up 5K, has 5,000 cells.
Mm-hmm.
And to think of that from a comparison perspective, a 1970s or like 1980s, a very small 8-bit microprocessor, start off like my favourite is the 6502,
mm-hmm.
that has 3,510 transistors.
Okay.
So if you basically have 5,000 of these more complicated LUTs, you can easily capture a 1980s microprocessor inside this.
Yeah, because a LUT can do far more than a single transistor. It's an entire logic
Way
block.
more.
So yeah.
So we're next on our journey. So I'll get this guy out. So Tim Ansell, I think probably inspired by the same things that drive Xeon. It was keen to basically try and create a very small FPGA that fit inside a USB port.
Mm-hmm.
And so this is called the FOMU, and it's in a series of little circuits. Tim's done. So he started off with an ARM processor. It was called the TOMU. Then did an FPGA, which is the FOMU, and I think they've now got a QOMU, which is combines a processor plus the FPGA.
Mm-hmm.
And so Tim was providing these FPGAs to anyone who'd like to run some workshops,
mm-hmm.
and so it's very capable, but one of the challenges it's very small. So
yes,
that was our first challenge.
Yes.
And
so for reference, that is designed to slide entirely inside a USB port. So it is so small that you put it into a USB port and you almost can't get it out again. It just disappears into it.
Yeah. So compared to back to where's these development boards? I've lost the it's here somewhere.
Hiding under the paper.
Who knows where it is? Oh, here it is. No, where's the one I had earlier? Oh, here it is. So
just a second. Dodgy says that we've got an echo.
Okay.
So I'm just having a quick look at where that might be coming from. Is anybody else having problems with the audio? One of the issues is that at the moment we've just got a single microphone that's hanging up here in front of us, and just hoping that can capture enough that we sound okay. No okay there, Peter? Okay.
Yeah, I've turned off my sound.
All right. Yep. Hopefully it's fine. Thanks, everyone.
Okay. So it was great that Tim was handing out these FOMUs to anyone who wanted to get into FPGAs. The challenge is it's much more difficult to work with than a development board. So that's a challenge. So just what's on this FOMU is you have the FPGA, which has all these logic blocks. I'll just put it around this way. You can see there's these 4 outputs. So there's 1, 2, 3, 4 outputs. It has an RGB LED, which we'll see in a sec, and also has flash memory.
Mm-hmm.
I think it's 2 megabit.
Okay.
And so to get this off the ground is you basically need to initially flash some bits to the flash memory, which then the FPGA will when you power it up will get loaded into the FPGA, and then that configuration will then have the FPGA do something useful.
Okay, cool. So this is getting to a critical point. And earlier on we were talking about LUTs as these logic cells which can be reconfigured. So in order to do that reconfiguration, with a normal computer you have different types of memory. So you have RAM, which is non-volatile. You have which is volatile. You have non-volatile memory. You load code. You can run it in RAM. Once it powers off, it all goes away. So conceptually, this is quite different. And so one of my questions I have is, when the FPGA is being configured, you're having to set up all of these LUTs so that they do their particular functions as you've defined them. That information has to come from somewhere. Is that like a write once and then it stays there? Or you're talking here about flash memory. Do you load it into flash and then from flash it gets loaded every time on boot up?
Yes.
Okay, so every time the FPGA starts, it loads the configuration from flash memory and then applies it to those LUTs?
Yep, that's the default situation.
Okay.
So this particular FPGA, the UP5K, inside also has some non-volatile memory, and so what you can do is you can let's start again. So what sits in the flash memory is what's called a bit stream, and so you load the bit stream into flash memory, which then allows the FPGA to do something useful when you power it up. Mm-hmm. But what this particular FPGA also has non-volatile memory, so you can actually then move what's in flash memory into the non-volatile memory. So I'll just basically boot off that non-volatile memory without having to need an external flash chip. But you still have to be able to get that bit stream into the FPGA. So basically, you've got this basically bootstrap problem.
Yes.
So that's the first thing you find with the FOMU is from nothing, how do you get it going? Mm-hmm. And so John and I had to deal with that problem, which I'll get to in a sec. Mm-hmm. So perhaps what the other thing to talk about is how do you create this bit stream? So let's talk about the whole process from the beginning. Mm-hmm. So let's get this out of the way.
Maybe just before we get to creating the bit stream, let's just zoom out a fraction. And sorry, I've just got to switch over here. So. And just for a moment, think about why we care about this. Like, what is the actual, what is the power of an FPGA, and why would we be doing it this way rather than, for example, having a traditional microcontroller, writing some code in C or whatever, and loading it. And so maybe you can talk about a couple of the advantages of what this gives you.
Sure.
And applications, things you would use this for.
So I think, you can spend your whole lifetime, your whole career without having to need to go to an FPGA. The range of chips we have from either LSI type chips like the classic 7400 series or the 5400 series, you can build anything out of that, and sometimes people do. People build whole microprocessors out of that logic. Yes. Insane, but awesome at the same time. Then we've obviously got our embedded CPUs. We've got obviously the big CPUs on laptop. You can just it's rare to need an FPGA. Mm-hmm. In fact, I would guess that most people come to an FPGA is I know an iPhone 7 actually use the UP5K in the iPhone 7 for low power operations.
Interesting.
So when do you need them? I think for me one of the initial cases is that you only have like a set of buses, like one I2C bus or one SPI bus or that type of thing. And so an FPGA, if you want to have a processor with 2, 3, or 4 I2C buses, you just add them in. It's as simple as adding writing a bit of software. So that's useful. The other thing is you might need to have lots of I/O, like maybe 100 pins of I/O, and it needs to be working at several. Tens of megahertz or even 100 mega input. And then
if you're doing digital acquisition of data for sampling sensors or maybe analog inputs, not just digital inputs.
And the other cases like Tim Ansell, I think one of his key applications is doing HDMI processing. So for Next Day Video, which drives all the video, the AV at Linux, the Linux conference, and so. That's similar to Bunny's project with the NETV2. If you want to do processing of those sort of digital signals at high speed, they're useful there. But these are sort of applications that are not typical for us.
They're not mainstream hobbyist projects.
Exactly. So I think what's interesting now is you can get very small FPGAs like the UP5K and smaller for just a few dollars, and rather than having to make a PCB and around a bunch of glue logic, you can just basically do that in the one chip.
Yep.
What's another interesting one is now the RISC-V processor, and so you can basically put a RISC-V processor onto this chip and play with RISC-V, and then add more things to it on the bus. So yeah, it's just super flexible.
Cool.
So,
and in terms of flexibility, one of the other things that I've seen a little bit of is being able to assign different uses to different pins. So to some extent, with some limitations obviously, you can put an FPGA on a board and then decide later which pins are going to be used for which functions.
Yep.
So you could potentially simplify the routing of your PCB by associating traces with the closest pins on the chip, or if you changed your mind and you decided, I want this serial port to actually be an I2C port, then you can change the configuration of those pins and use them for a different purpose without making any changes to the electronics at all.
Which is a similar situation to a modern microcontroller like an ESP32, where you've basically got the pin mapping, so you can attach the
that's true.
The hardware peripherals like SPI to
they have mappable pins. Yeah.
So I think the problem with FPGAs is just the barrier to entry. It's no longer cost. These things have got a range of cost and power and so on. But it's just that I think the vendor's toolchain, they're quite I guess Baroque and Byzantine in some respects. I think to get a lead flashing was the most expensive and time-consuming effort ever, compared to like an Arduino where you're going in just a few minutes.
Yeah, well, this reminds me of the situation when Arduino came along. Like if you think back to say 15 years ago, back in the days of microcontrollers around then, you would often have to pay for an IDE from a microcontroller supplier, and it might cost thousands of dollars to get the software set up. And then you'd be paying hundreds and hundreds of dollars for a dev board. And then, of course, Arduino revolutionized all of that. Arduino wasn't the only project, but that's really the figurehead, I suppose, project that drove it.
Yep.
And so now we're in a situation with FPGAs, which is a little similar. It's expensive vendor tools.
Actually, if I can interrupt, the vendor tools are pretty much anything you need on a hobbyist level are all free, because otherwise the chip's unusable.
Yeah.
So no, so the tooling is free, and there is obviously a professional level of for support and stuff. But no, but it's really, I think for me it's the difference between using pre-open source tool chains from a vendor, which are always a bit weird and wonderful.
Yeah, you're forced to do things their way.
Whereas but now with Arduino, and since then open source tool chains are just it's like working on a desktop. And the same revolution is now happening with FPGA. So I think it's when you talk to some FPGA people, they're just so excited to tell you about it. It's like you should be getting this, but the barriers to entry are so high. And I think due to Tim and Sean and other people, that they're now changing that. So just talk about the open source tool chains. It would also be good to actually get you into something before we run out of time.
All right.
Did
you want to draw some more diagrams?
Yeah, just to overhead. Yeah, so have we got any interesting questions there? Or maybe just check. Yeah, okay. So what you want to do is you want to start with some a description. A description of the logic, and that's typically done in a language called Verilog, or in VHDL. And these are languages that are very much. Hang on, I'll just move this.
These are
languages that are very much inspired by the C programming language. And so what you're doing is you're basically describing your combinational logic and your sequential logic in these languages. And so it looks a little bit like C code. We can show that in a sec. And you basically take this.
Hello, Astra. For those of you, you can't see her. She's down the bottom, but we have Astra here as well.
Yeah. And so what you need to do is that gets turned into effectively an intermediate format. And this is basically called synthesis. And this intermediate format basically says takes your combinational and sequential logic and says here's all the cells that'll be required, or effectively your LUTs, and here's how it basically turns the C code into your your lookup tables and your flip flops and all that sort of stuff. Yeah.
So So the toolchain should be hiding that very low level part from you. Yep.
Yeah. And this will be tailored to what each of the FPGAs provides in terms of number of cells and how so. Then the next step after that is what's called place and route. And so you've now got these cells. So you've now basically got to say how do we select them out of the FPGA, and how do we start to route them all together? And there's also these big common buses.
Yep.
And that produces another file. And the final step is then basically generate the bit stream. And one of the problems with the bit streams is they're typically proprietary. So Xilinx and things Altair and these other companies, they don't publish the format for their bit stream, which is unfortunate. But fortunately, one company, Lattice, which produced the UP5K, they basically publish their bit stream format as open source. And so basically there's tools to basically take the output of the place and route and generate that bit stream into a binary file.
Okay.
And people have also now have reversed the Xilinx format to some extent and so on. But the key part of the open source toolchain is these first parts, and sometimes either use open source for the generation of the bit stream, or sometimes you still use the vendor tooling to basically get it onto the FPGA.
Yeah.
And then the open source project that sort of brings us together, the best known one, is something called why's the name escaping all of a sudden? SymbiFlow. SymbiFlow. And what first step to get this loaded onto John's environment is there's a project called OSCAD Suite, which basically brings together all these open source tools into a single simple download. So we're going to basically try and get. So you can try and build SymbiFlow from scratch. So this first part's called Yosis, which is the compiler to compile Verilog into this intermediate format. Place and route is something called Next PNR. That was a second generation place and route. And then all the Lattice tools, there's a project called Ice Storm. And so when you first confronted, let's just get this back onto the screen a bit, this Ice Storm. So when you first confronted all this, it's a lot to sort of...
it's a lot of pieces.
A lot of pieces to take into account. But now, but over the years, people have brought this all into things like SymbiFlow and OSCAD Suite, and package it up for you. So let's perhaps try and do that. So
okay.
So let me just go to my notes. So let's see if we can get John going. So we want OSCAD Suite. I've got some notes on my machine.
Okay.
So if we want to go to where is it? Where's the download?
All right. So I will need to be downloading something.
Yep. So let's go and download that.
Okay. Well then, we can.
I'll just select this too.
Switch to here, and I'll do this.
Okay. So there's
on screen. Oh, you can't see us now. Oh well.
Okay. So I'll just select you the GitHub link to a project called Yosis HQ, Yosis headquarters, and they create OSCAD Suite build releases. So see if you can.
I just need to find where I put that Slack window. Oh, there it is. Okay, here we go. So I will copy that, and so it's this one. Let's put this in the chat as well. I'm just going to drop it in the chat. So that's what I'm currently going to. All right, so this is the place to get the OSCAD Suite. And I guess I want the Darwin x64 version.
Yep. And if you're running on Ubuntu, I do all my development on an Ubuntu machine, so I pull down the Linux AMD 64, and also work on a Raspberry Pi, and we can talk about that a bit later.
Okay.
So you just choose the one you want.
Yep. So that's downloading. Oh, is this all okay on an M1 processor?
Ooh! Oh, you'd want the ARM.
Oh, the ARM version. Okay.
Oh, we are on...
Oh, that's Linux ARM, but there's no
Darwin
ARM.
Crap.
All right.
That's problem number one.
Well, we can...
We don't have time to build it from source, so that's a bit crazy.
So we can do it on your computer, though, can't we? And we could capture... We can capture this screen.
Yeah, okay.
So maybe we'll switch to a plan B.
Okay.
So
here's one we prepared
earlier.
Literally. Okay.
All right, shall I switch to your screen?
Yeah, sure.
Yeah. Okay. So what we're looking at right now is Andy's laptop.
Yep. And so I've previously downloaded. You basically just download OSCAD Suite and just tar unzip it, and you end up with a directory that looks like this. And in there's a bunch of binary files. So let's have a look at that very quickly. The dog is underneath my feet.
Astro wants to be in the show.
Okay. So you can see there's a lot of binary files, but a key one is DFU. That's the there's a standard for devices for basically loading firmware devices over USB. This could be a mobile phone, it could be all sorts of devices. And just so it turns out that Tim and his team for the FOMU basically decided to support DFU format, so you can basically use DFU to load the bit stream onto the FOMU over USB. She's raiding your boxes. Okay, so that's that.
Empty rubbish bin.
What else is interesting here? So GTK Wave. So that's a really good diagnostic tool. So you've got all these signals inside the FPGA, and what you can do is there's tools that allow you to capture those signals, and then use GTK Wave to display them, with the name of the signal, and that's pretty handy.
Very useful for debugging.
Yeah, so is that. Let's go a bit further. There is all these ICE tools, like so the latest range of FPGAs is called ICE, and
just a second. Robson said it will still work on the M1 Mac as it can run Intel-based programs as well.
What one we go?
That's interesting. So
thanks. Right. Let's give it a go.
All right, I am going to at least extract this.
Yep.
So
all
right. In the meantime, we will continue on this one.
Yeah. So all these things like IceProg, they're the upsets tools for like programming the latest series of processors. There's another set of tools for doing Xilinx and so on.
Okay. So is ICE for lattice, of course.
Yes.
Finally clicked in my brain.
iVerilog is there's two debugging, two sort of simulation tools. So typically, FPGA people will start by working in simulation. It's just so much easier than dealing with the hardware. And there's a lot you can do in simulation with modern fast machines. But personally, I always like to play with the hardware. I want to go. What's involved in actually getting a working thing going? And so certainly started off with simulation, but I like to get straight to the hardware if possible. There's next PNR, which is place and route, and you can see that there's the place and route version for the ICE 40. ECP5 is another lattice device. So you do that. Open FPGA Loader, that works with OpenOCD. Anyway, we're probably getting down into details too much, but just to finally finish up, you can see there's Yosis, which does the synthesis. So you start off using Yosis to synthesize your Verilog. You then use NextPNR to turn that into a bit stream that can then be downloaded. Downloaded DFU tool. So that's what that is. So let's just run that now, get that environment now. So SU go OSS/environment. And now I've got those tools. So basically, there's Yosis, for example.
All right. Now I am. While you're doing that, I'm just going to. So all I've done so far is download and extract OSS CAD suite, and so I need a shell in there. Is that correct?
Yep.
In the directory.
Yep.
OSS CAD suite. Oops. All right. I will. That look correct? Oops. Okay, so, oops. I'm just going to switch back to this desktop for a second. And now we've got, so I should now have the same as what we were just seeing on Andy's laptop. And it looks like I do. I don't know if any of these binaries are actually going to run, but hopefully Robson is correct. And this is working. So what was the command that you did to get the environment?
So you just go up one directory, up one level.
Yeah.
And just go source environment.
Source environment.
Yep.
Like that?
Yep. Hit return.
Cannot be opened. Real path. Okay, I'm just going to... No, I don't want to move it to the bin. I've got to get through these security authorizations. I should be able to do that. Where are we? Security and privacy. Allow anyway. Hopefully I won't have to do this too many times. Let's try that again. Source environment. Open. And is that it? Did it run? I don't know.
Just try typing Yosis and see what happens.
Yosis. Oh, it's going to do this for everything, isn't it? So now I've got to allow anyway. This is a oops. No, cancel.
While you're doing that, I'm just going to try and get a...
I think this is something that is going to be frustrating to work through the first time, and probably not something to do on a live stream, because I'm going to have to be doing this for everything that it asks to open. Once I get through this the first time, I won't have to do it again.
Yeah,
a couple more.
Oh, is this the phone?
Oh, anyway.
Hey, little girl, what are you doing?
Alright, I'm going to switch back to Andy's laptop.
Okay.
I think.
Yep, I was just going to try something whilst you're doing that.
Yep. Okay. Well, anyway, while Andy's doing that, I'm just going to sit here and keep hitting allow.
Okay, cool. Alright, so going back to my laptop, or?
Let's see, it should be, but yes, there we go. Okay, back to your laptop. Yep. So far, I haven't got Yosis running, but I'll just leave that and see what happens.
Okay.
Don't extract it in your downloads folder, says Mark. Yes. I will try moving it while Andy is doing more useful stuff.
Oh, you still watching my screen?
Yes, it's on your screen now.
Okay, cool. So what I've just done is I've just logged into my Ubuntu machine. So you can see it's that's it. And I'm running the OSCAD suite now. And so I just plugged the FOMU into the USB port of that machine. And so if I go DFU-L,
I've just got Yosis coming up.
Awesome! Wow, we're multitasking. I don't know if everyone can keep up.
I'll just switch briefly to my screen. So after hitting that allow and authorize many times, I have finally got Yosis.
Okay, so if you just do a quit.
So I'll just bring it up so that you can see it on the screen there. So I'll quit out of Yosis.
Yep. So that's the first program. And if you do next PNR.
Quit did not work.
Oh, just Control D then maybe.
Okay.
Yep. So you can now do next PNR. Just tab. I just go like ICE.
ICE 40.
Yep,
this is probably going to do the same thing. It's going to ask for authorization.
Oh man, this is super painful.
Yeah.
I'll let you work that out. Anyway,
yeah. All right.
And then the final one might be like DFU-Util. We definitely want to see DFU-Util.
Yeah.
Like in fact, what I'll do is I'll throw let's see, where is it? Here it is here.
Alright, so what I should do
DFU-Util work
is do DFU-Util
-L.
Oh, -L.
Oh, it doesn't matter. Just
I've got to go through this.
Is no way you can just do an all?
Probably.
That's crazy.
Oh, I think because it's forking extra processes, so each process it wants to get authorization.
Right. So so now what we have to do is if you can plug this extension USB cable into your Mac.
Yes.
Mac.
Okay.
Yep. If anyone in the live stream knows how to get past having to press OK on all those dialogues, that'd be great. Now, so if you just do the downward camera for a sec.
Yes.
Okay. So this is an extension USB cable off John's machine. I've got a FOMU and I'm just about to plug that in. And in it goes, and you can see it's doing a nice little welcoming glow.
Mm-hmm.
Now if you type DFU-L again.
-L.
Yeah, there it is.
Okay, I'll just switch back to my desktop so you can see what just happened. So I just ran DFU-Util -L, which I assume is list.
Yep.
So it's finding devices and it's found this particular device, which is the FOMU that we just plugged into that extension cable.
Yep.
So looking good.
Yep. And so you can if you only had a bit stream, you'd be able to do a -D for download and download that bit stream. So that's a nice step.
Mm-hmm.
Okay, so
Robson was correct. The tool seemed to be working on the M1 Mac.
Well, that's a win. Okay, so next thing we can do is let's see. Should we go back to step? Okay, let's always start at square one to say how we got to this point, because there was a step. So I'll get another bit of paper out. This is kind of a really taking people through the weeds. Right, good enough. We've got down. Okay. So you may recall before that I sort of said there's the we've now got our laptop, or that's talking over USB to the FOMU.
Tiny laptop, huge FOMU.
So this is our FPGA, the up 5K, and we're using the DFU protocol, and what we've got is basically the D plus and the D minus from the data pins from the differential data from USB.
Yeah.
That's going into the FPGA.
Mm-hmm.
And then hanging off that, effectively SPI, is the flash memory.
Okay. So you talked about the D plus and D minus pins here going into the FPGA.
Yep.
And we've talked about how FPGAs can be reconfigured to have different peripherals.
Mm-hmm.
In this case, do we have USB implemented virtually, like within the
Not
FPGA,
at
or is
all.
it dedicated hardware?
So the short answer is no. The FPGA has no USB support.
Okay.
I'll put a couple of resistors in there just to.
So is this where we have a bit of a bootstrapping problem?
Exactly. so just this is a quick aside. What people often do is they basically have an FTDI. Is that right?
FTDI.
Yeah. That FTDI. Always get that around the wrong way.
Yeah.
They have an FTDI chip which basically goes USB on this side,
Mm-hmm.
and it's obviously serial on the other, and then they'll have their FPGA there.
Okay.
So that's a very
the classic way of doing it.
Yep. Or the other is they'll basically have a way of basically talking directly to the flash memory.
Okay.
And basically talking SPI.
Ah.
So these are. Oh, hang on, I'll just move that into view.
Yep.
So our FOMO situation is this, where we've basically got no USB support and just wires going to the FPGA.
Yep.
So it's kind of cool, but difficult. The second is to do FTDI serial to get the FPGA up, and the third is basically talk SPI directly into the flash memory.
So if you look at that sequence, the options 1, 2, and 3, the third option looks like the most low level in terms of if you're not interacting with the
Yep.
FPGA at all you're doing is talking to the flash memory saying here is the bit stream, store it.
Yep.
And then it gets loaded.
Yep.
With option 2 you need support for that serial interface
Yep.
within the FPGA, and with option 1 you need support for USB within the FPGA. So it's
And then you've got
increasing,
nothing. Yeah.
it's moving up the stack a little bit.
It does, yeah.
Mm.
So just through some magic we're about to describe, this FOMO here, which is actually flashing on the screen, so I'm not watching what. Yeah. That FOMO is actually, I'll just cut to the chase. It's basically got a soft RISC-V processor, which has got a USB stack running in C, listening to those ports. So
Okay.
that's what's going on there.
Yeah.
It's all basically being done in software.
So it's layers on layers.
Yeah, layers, exactly. But you basically got to get there, and that's the trick. So we'll just quickly describe that now, just for completeness sake.
Okay.
So what you have to do is this. That okay, I
It's
can
a
see.
little bit hard to see
Yeah,
because it's
so
black.
there's instructions on the web about how to do this, but inside there's these pogo pins. So John 3D printed this enclosure, connect the pogo pins up to wires, and what you can do is you can take the FOMU. I'll just pull it out of here. You basically take the FOMU, push it into here, and hold that down whilst you have something that can talk SPI. So it could be typically a Raspberry Pi. So you basically you get your Raspberry Pi, put these all these cables on here. Here we've actually got from the web. We basically got that and said here's the GPIO header, and these are the wires you've got to connect to get SPI from the Raspberry Pi.
Yep.
And then what you can do then is you get the bit stream and basically flash it directly onto the flash memory of the FOMU.
Okay, so what we're doing here is number 3 out of those options.
Exactly,
we
yeah.
showed us earlier.
Yeah, so basically get ourselves off the ground. I don't know if this is possible through the microscope, but there is very tiny...
we can't use a microscope at the moment because I stole its HDMI for your laptop.
Okay. Okay. Well, you possibly see there's some very tiny test pads on there. And the first time to get this up, I basically soldered wires onto the test pad and was able to flash flash the FOMU investigator up laboriously, which gave me enough confidence to say, John, hey, let's do this 3D printed rig so we can do another 50 of them.
Yeah.
Anyway, so anyone got any questions? That makes sense. So what you do is you synthesize your first bit stream, which knows how to it has this RISC-V process with a C stack that knows how to implement the DFU protocol, which then allows it from then on to just be able to flash it after that from USB.
Okay.
Which is really very handy.
So you push that in using method 3 over SPI directly to flash. The FPGA starts up next time it loads from flash, begins executing the software, the soft core, which then implements USB, which then allows us to use method 1 and talk directly over USB.
Yeah, so just in terms of stack, you basically have...
I got a very handy hint from Robson. Said open Mac settings, head over to security and privacy, then go to the privacy tab, scroll down to developer tools, unlock padlock. Thanks, Robson. You've been very helpful today, so I will do that.
Well, yeah, if we do that, we can keep pressing.
Yeah, I will do that while you are
all right.
explaining that.
Okay. So what we have is we have the flash memory, which we'll just talk to over SPI. So it's SPI to get our bit stream in there, and then what that has is it has a RISC-V CPU, and it's only the equivalent like an ARM Cortex M0. It's not the one that can run Linux or anything like that. It's just a very tiny 32-bit RISC-V. I think it's basically it's an RV32 or something like that, RV32i. You also have like if you like a small BIOS. So that's basically C code, which is just enough to boot for the. It's basically like putting C code into an Arduino. Basically, there's no operating system, just pure C code.
Yep.
And that's basically then on top of that, basically that gives you your USB stack and the DFU protocol, and that's literally listening to the D plus and the D minus pins of the that's going straight into the FPGA, and that's effectively what we've got running here. And basically the other thing it does is if I push it in properly, pull these things apart.
So there's a fair bit of magic that's happening there, because what we're talking about is the actual literal differential signal wires coming in as two I/O pins. And then, of course, you've got to deal with the timing and all of the low-level USB stuff, which is being handled within the code running on that soft core.
Yep. Yeah. So it feels like a lot of messing around, but what it does is it's really lift us up to a level now where we're working with a RISC-V process. You can compile C code for it, and so it's a big barrier to entry, a big leap. But once you're there, it's really accelerated the power of what you can do with the FPGA.
Yeah.
And that is called FOBoot. So let's find the URL for that.
Okay.
Just search for GitHub FOBoot.
Okay.
And so Tim Ansel and his team wrote that, and that's used by a number of FPGA projects now. Anyway.
I'm Tomu FOBoot.
Yep.
Oh, it looked like what was this one? FOBoot hacking at master. Oh, that's the same thing.
Yeah, you want that first link.
Yeah. So this is the FOBoot project. The bootloader for FOMU. So it exposes a DFU interface to the host, software half and hardware half. All right.
Okay. So for workshops and what we're intending to do is, but you would already have FOBoot on the FPGA, so that you're basically just compiling you're basically synthesizing bit streams and just DFU util and flash it. So let's see how we're going on time. Hey, not too bad.
Yeah.
So let's see if we can get flashing LED happening.
Okay.
On your laptop. Okay. So next thing to do is to download the FOMU Workshop. Is probably the best place to go. So just go GitHub. I'll see if I can find it. Find it on my machine. Oh, if you
should I just search for?
Yeah, you can search as well.
GitHub FOMU Workshop.
But I'll also find it. I'll look for it at the same time as you are.
Okay, looks like this is it. I'm Tomu FOMU-Workshop.
Yep, that's it. So if you just git clone that.
Okay. Code. Copy that. And where should I? Oh, I'm in my downloads folder at the moment. I probably should not be there.
Not the downloads folder.
Okay, I am just going to make a another folder and move this over, do some zoomage. Right, git clone that.
Okay. I'm also just going to Slack you the actual workshop URL, so that might be worth saying that.
Okay. Yeah, it could be useful to be putting this in the chat as well.
Yeah, I can do that.
And later, after this live stream, I can update the video description and put in some of these useful things too. So the URL of the workshop is right here. So do you want to explain what this workshop is? Because could be a very, very useful resource for people.
Oh, it's a fantastic resource. So what we'll quickly do is I'll just quickly show some Verilog.
Okay.
So we go into HDL, Verilog, Blink. So Verilog files .v. So this is some Verilog. Hopefully, actually might.
I can move this out of the way.
So I was just going to move my screen if you like, but that's okay.
I'll move this over here for now.
Yeah. So the first thing we do, so it looks a lot like C. So the first thing we do is basically define some pins for the red, green, and blue inputs to the LED.
Mm-hmm.
And then next after that, you in Verilog everything's done as modules.
Mm-hmm.
And so you have a top level module that can reference other modules, and so you basically use that to decompose your project into various things. So into it can be low level blocks. Like you can have like a module that represents the I2C or an LED or some PWM or that level. Mm-hmm. It could also be something if you're building a CPU. It might be like your it could be the CPU, the memory, the arithmetic logic unit and that stuff. So this is just a way of decomposing things down to modules.
Mm-hmm.
And then with your modules you have inputs. So in this case our top level module has input, which is the clock.
Clock high.
And then it has outputs, which is the 3 RGB pins, and also has pins for USB.
Mm-hmm.
So this is this module called top. Now on the FOMU it has a 48 megahertz clock, and this is a bit of a diversion, but in FPGAs you can have different clock domains, so you can have different parts of your circuit running at different speeds. Mm-hmm. And so what's handy about 48 megahertz is that nicely divides down to 12 megahertz, which is USB-C.
Yes.
Yeah, so basically, what the reason it has a high speed 48 megahertz clock is it means it can sample the USB pins.
Yep.
To see if they're high or low. Mm-hmm. And then the actual RISC-V processor and everything else is running at 12 megahertz, because what you find is that it can be quite hard to, as you get more and more complex logic, it can be quite hard to have the FPGA running at high speed. So we basically have these two clock domains: a high speed domain for sampling USB, and then low speed 12 megahertz for everything else.
Okay.
Yep.
So I'm just going to jump back to a bit of a meta question here. You're talking about clocks and how these blocks. In this particular case, it's got a clock input and it's coming from the 48 megahertz clock.
Oscillator?
Oh, oscillator. So what this raises in my mind is I think of the execution of code within a microcontroller as being very linear, particularly in a single core,
sequential one after the other. Yeah.
It's in a very single core sort of way. Whereas what we're talking about here is logical blocks which might be operating off the same oscillator or clock independently. So you can have one block which is reading a USB port, for example. You could have another block which is reading a different USB port, and they can both be executing at the same time. It's not a sequence of operations.
Oh, it's the fact of myself, the other logical end of the extreme. If you're running in Python or JavaScript, many of these scripting languages, you're pretty much working single-threaded.
Yes.
Maybe for a systems person working in C or other language, you might have some multi-threaded thing going on. But a lot of people these days, especially like when doing web development, you're working typically in one thread. Whereas everything's going at the same time. So if you've got 5,000 lights or cells in FPGA, on every clock of that 48 megahertz clock, they can be all changing state if you wanted to.
Yeah.
Which is means massive parallelism. You can get quite a lot of performance, which is great, but also means it can be a bit of a mind bender if you're just used to one thing after the other.
Yeah. So to really get the benefit out of this, you need to think about things a little bit differently to a traditional sequential sort of programming model, and think about the problem that you're trying to solve and how it can be broken down into operating in these blocks. Is that part of the whole design process?
And I think it's the easiest way. I think it's this thing of we've got a big state machine, and so basically going on each clock pulse, you're going from one state to the next, and within that clock pulse, you go, what are all the things that are changing, and even though you've got the potential for everything to change at once, you don't really necessarily want that, because that's, you may not need that complexity.
Yes.
So let's just look at how this looks like in the code. In Verilog, you can have either what's called a register, which basically can maintain some states. In this case, it's a counter, or you can have what's called a wire, which is really just a connection between two cells. And so what this is saying we've got a 29-bit counter. I think it is going to goes from bit 0 to 28.
Okay.
Maybe it's 20. No, I think probably it's 28-bit counter. I think. Yeah. So it's got 28. So basically, you define the number of bits wide the register is, and we're going to initialize it to 0. So it looks a little bit like C. And then what we're doing is saying, whenever there's a positive clock edge, you basically want to increment the counter. And so that's looking a little bit like C code, or like a high level language.
It does a lot.
But what's amazing about that is that turns that counter increment, counter equals counter plus 1, into all these sequential logic to actually build an adder.
Okay, so it's implementing the adder in hardware essentially by defining the gates that compose that.
Yeah, and so if this was just a 1-bit counter, or it's like a 2-bit counter, we could probably just by hand figure that out. Basically, you could do the little lookup table and go, right, if it's if your input is 0 and we're already at 0, then the output 0. If the input is a 1 and we're a 0, then it's a 1. We can figure that out.
For the first couple of bits, you could design it on paper.
Yeah.
But beyond that, it becomes very complicated.
Yeah, or it's just laborious, really.
Yeah, that's right, very repetitive.
Yeah, and so if you want a 64-bit counter or a 128-bit counter, just change that variable. So it's very powerful that way. Now the other thing that which we haven't discussed earlier is that if you have to do everything in the cells, that's complicated, slow, and so quite a lot of FPGAs provide what are called hard blocks for useful things. So if the UP5K has a hard block for has two for I2C, so you have two I2C buses in hardware.
Okay.
It's got 2 SPI. It also has the LED drivers. So basically, it has a current limiting LED driver.
Ah, right.
Which is nice.
Yep. So you can do onboard current limiting without having to try to do anything complicated with, say, PWM and external resistors and that sort of thing. It's all just built in.
Built into this into this one. And the other LED driver's got for doing effects like pulsing and like this nice breathing sort of sequence. And so we can see that here. And so SB stands for system bus. And so this basically is a like if you like a block, an FPGA block, but it's not a soft block like something we code up ourselves. It's called a hard block. And so this is for the RGB driver. So basically we can say what our current mode is. So it's basically going to be 4 milliamps to every pin, red, green, and blue. And here we can basically say we want to drive the RGB colors by the counter. So basically we're going to basically for the red pin, we're going to take the 25th bit of the counter and have that tied the blue. Sorry, I said right. I meant blue. The blue pin of the LED is going to be attached to the 25th bit of the counter. Okay. Yes. And the red pin is going to be attached to.
I see what's going on there.
Yeah. So basically, what's happening? We're going to basically get in color sequencing.
Yes.
So this counter is basically going to be going at effectively 48 megahertz.
Yes.
But by choosing bits inside the counter, we're basically going to
find the rate at which that's going to cycle.
Exactly. And so these bits are actually kind of very close to the top end. So so basically, it'll count to many millions before these bits change.
Yes.
So
but at 48 megahertz, many millions is not that long.
Exactly. It's going to be like several times a second.
Yeah.
Yeah. So that's basically Blink done in Verilog. So let's see if we can.
Okay. So another meta question. With this example code that you're showing, which is in Verilog, is there standardization on the language side? Like, is Verilog the thing that everyone uses? Because I think there are alternatives, aren't there? Yeah, Verilog is only one of the ways of defining
Yeah,
it.
well, the two main ones are Verilog and the other is VHDL, and they're the similar level of abstraction, sort of based around C, but there's different. I've mostly just been using Verilog rather than VHDL.
Yeah.
And there are standards, and so these languages go back to like the 80s, and so over the decades there's been improvements in standards. There's also a thing called System Verilog. Oh, the other complication is when you're doing things in simulation. You've got your laptop, your host machine, and so you can basically do things like debugging. So you want to basically put debug statements out to your console. You want to do that sort of stuff, and so there's statements that you can use in simulation that isn't available when you're in the hardware.
Like you could set a breakpoint, for example, pause operation, then examine.
Yeah,
the
that
state.
sort of stuff. Yeah, and there's a program called Verilator which allows you to do those types of things. So that's all the language. But the really interesting stuff that's been happening over the last few years is rather than having to work in low-level Verilog, so imagine writing a CPU in that, and people do. Yes. Let me just show you that.
Sure.
Because I do like my 6502s. Here's a 6502 in Verilog that will fit onto. There's a whole 6502 plus. Basically, it's effectively equivalent to an Apple II.
Yes.
In Verilog, so basically you should be able to go and do. Yeah, I won't get too caught up in this because it's pretty amazing. But but if we go into actually, this one's just jumping ahead a bit. I'll go to my other one.
Okay.
Yeah. Oh, that's something else I should mention. Do you want to on your browser quickly find Open Cores?
Yes, I shall.
Yeah. Do you know? Have I told you about Open Cores? Yeah.
You have. But before we do that, I just want to stick to this whole Verilog thing a little bit.
Yep, of course.
And that ties back to something I was going to bring up earlier. You mentioned soft blocks and hard blocks. So just to reiterate and to make sure my understanding is correct, a hard block is an implementation of a specific function within the electronics of the FPGA,
yes.
And it is dedicated to doing that one thing, which could be something like a USB interface or an I2C interface, and you can't just totally change it to be something else. It is defined to do that.
Yeah, but within the code, you reference it as if it's just a module in Verilog. It's just another module,
it's like
effectively.
So it's very convenient. So that means that. So this ties into the question I had about Verilog, which is when you are targeting different FPGAs, you have to understand the capability of the target, both in terms of the number of LUTs and what hard blocks might be available. So you don't call, for example, a hard block that doesn't exist on the target device. And so because there are multiple manufacturers, so there are many manufacturers that make FPGAs that you can configure with Verilog, is that correct?
Yep.
And so and I'm just in my head, I'm trying to understand the scope of what I need to understand to write something in Verilog and be sure that it's going to execute on the target that I have in mind. Okay,
so as long as you're sticking to combinational and sequential logic, it pretty much is portable across all FPGAs.
Okay.
It's certainly I suggest the two key differences are how you synthesize that Verilog and get it onto the machine. So like with vendor specific tools and stuff like that. And whilst I personally prefer the open source stuff, the vendor tools obviously work with their FPGA much better. So professionals are going to be working in the vendor tools typically. There's a lot of optimizations and speed ups they do for you. But one thing the open source tools have got over the vendor tools is they're very fast. So
really?
Yeah, it's surprisingly. So something might take half an hour or perhaps multiple hours to synthesize the Verilog into something a bitstream using a vendor's tool. We might sometimes just do in 5 or 10 minutes in the open source tooling. It's that much faster. Yeah. My understanding from just reading is that there's less I guess pressure on the vendors to basically make their tools go faster. It's kind of weird. You think they want to optimize a professional engineer's time, but
so they're optimizing for a different thing, maybe for more efficiency in the output, or is there some trade-off that's happening in order to achieve that speed?
Not sure. I suspect there's lack of competitive pressure. Like if the only person making a tool for your hardware, then
is you.
I know it's weird, but anyway, that's the situation. But I just wanted to quickly show this thing on the screen. Is on the right. That's the Verilog to do a complete 6502 processor, and it's
I see on just put a thing in here saying iStudio exclamation. So do you want to mention iStudio, or is that how that fits into all of these things we're talking about?
iStudio is Lattice's
that's their
proprietary chain. Is that where you? Go Peter, yes. Hang on, wait a second. Just downward facing camera.
Okay. Here we go.
There we go.
For the 6502 fans.
Yep, so where is it? So basically 6502 ROM, RAM, and an Arduino that I use to basically load up the RAM.
Okay.
Yep. And there's a little digital oscilloscope and a parallel port. So basically a full 6502. So that's a sort of a side project.
So 6502 on a breadboard.
Yeah. The thing is, if you want to share that project with other people, that's a lot of messing around, hours and hours of work to build that. Whereas if you basically do it with an FPGA, so like what we're doing here, means you can share 6502. I guess nostalgia with on a $6 FPGA and just all in software.
Yep. Sorry. We'll get back to your 6502. Sorry,
yeah.
I diverted you there for a while.
That's okay. No, that's all. We've got more squirrels. So this basically just to show you what the Verilog looks like for a whole CPU. You basically say there's a CPU module and the inputs are things like the pins we would expect on a CPU, like clock and reset. There's the address bus, the data buses, IRQ. So these are all just recognizable pins from a microprocessor.
Okay.
Oh, actually, they're all written here. Mm-hmm. And then it just goes from there for another 1,000 lines. Basically, you've got your program counter, your address buses, and there's your processor status flags. Mm-hmm. So it's more or less readable. This is 6502, and then just goes on and on. There's that's going to be our effectively almost like an internal. I say microcode, but it's basically like an internal state machine for all the instructions broken down.
I see.
And just goes on and on and on. So it's just possible to do this, but it's pretty laborious.
Yes.
But to get back to the thread was following was that what's happened over recent years is you can now use high level languages, Python, Scala is another one. So there's tools in Python called MyGen, and in Scala there's Chisel and I forgot the other one, Spinal. And what you can do is you can actually write Python code that describes your combinational and sequential logic in your modules, rather than writing in Verilog. And so you go, well, okay, we've gone from a C-like language to a Python-like language, but it gets better again. Above MyGen, there's projects like LiteX, and basically when you're working in LiteX, you're basically constructing whole systems on a chip. So basically, you say I'll draw a little picture.
Okay.
So with let's see how I'm going to do this. So something like MyGen. This is a Python project that allows you to basically turn Python into, well, not exactly Verilog, but into
Verilog-ish.
into the
format.
Yeah, and what you can also do is it does support. So basically, you have all your modules like in MyGen, if you like, but also it also can support including Verilog modules. So if you want to just write some very tight Verilog, you can do that as well. So
this would be
V.
This would be a little bit like if you're programming in C, you can write some stuff in C, and then you can bring in some assembler for optimization.
Yeah. Or you can work in Python, and or you bring bits of C.
Yes.
Yeah, so the same thing. So that's working at that level. But then you can use something like LiteX, and what that does is that allows you to work at the level of basically SOCs, where you basically go, we're going to have a bus, and a very common bus is called the wishbone.
Aha! I've been waiting to hear about this.
Finally get to the wishbone. So that's basically a 32-bit bus, and it's basically using memory mapped I/O. And basically you can just hang all your peripherals off there. So basically you can have you can have an I2C block, an SPI block to hang your peripherals off. You can have some RAM, some memory. You can do something that's a bit custom, which basically means you're basically bringing this into here, and you can write a little bit of Python that basically just describes your system, and off you go. And also you can put a CPU, like a whole RISC-V CPU in there, and all these things just appear on this bus as memory. And then the other cool thing about this whole thing, is just going to give myself a little bit more space, is you can then have your laptop sitting over here, and basically USB. And so you can basically you can peek and poke everything on the bus from your laptop, basically using what's called the wishbone tool. And hopefully we'll get to that point today. And so you just use this. So basically, you just use a CLI command to peek and poke memory to drive these peripherals.
Okay. So there are so many layers involved in this.
Yep.
It's all built up from the very low level LUTs, which are the basic logic gates, all the way up to
down
what we're talking about now.
Yeah, so down here you basically have your LUTs and your flip flops, or basically these are called they're sometimes called configuration logic blocks or just logic cells.
Mm-hmm.
So yeah, basically you've got thousands and thousands of these, and then these layers. And but what that does mean is and this is getting back to the FOMU, back to the FPGA Workshop. So if you maybe just bring that back up on the screen, let's go through.
So here we have the FPGA Workshop.
I'll have a look on my screen. So if we basically click on the Python on FOMU.
Let's just give the explanation of what this actually is.
Yep.
So this workshop came about, I think mostly it was Tim Ansell plus
Sean
Cross,
and others,
and there were a number of others as well involved, who put together a whole lot of material, including FOBoot and some of the other tools that we're using today, and put it into a workshop format so that you can learn about a whole lot of this stuff. So this is a really interesting resource to have a look at. So from here,
I'm going to steal your extension cable again for a moment.
Go for it. And I will drop this the URL for this in the chat. And just coming back to what was in the chat, Sion clarified what he was saying before. No, he said open source GUI FPGA programming tool. This is iStudio.io. So we were talking about, was it iStorm?
Yes, iStorm. Yeah, I confused the two. Yeah, iStorm is the open source. Sorry, iStorm and iStudio are the open source, and they just have their other. I forgot what its name is.
Yeah.
I just simply don't
Very
remember.
Very similar names.
Yeah. Thanks, Sion.
So as Sion put the link in there, iStudio.io is the open source FPGA programming tool.
Actually, while we're talking about Sion, let me just see. It took me a long while.
Switch back to. Where should we go? That one, I think.
So, Sion, I know for years you've been driven to create very small, tiny picos, and I finally figured out the reason is you want them to be small enough to basically be able to stick up a squirrel's butt. So,
camera's over here.
So inside Evil Steve is a tiny pico driving his evil eyes. So
here's an Evil Steve. We already have an Evil Steve. This is
Frankensteve.
Frankensteve, yes.
Yep. Anyway, back on topic. So with the if you bring up the web browser for this workshop, so what this workshop does is assumes you've got a FOMU or any UP5K, which has basically got the FOBoot already installed. So it's you can use the DFU commands. Mm-hmm. So you can then if you click on the Python link
over here, Python on FOMU.
Yep, here we go. So one of the first things you can do is basically just take basically compile a MicroPython in the C version of it to RISC-V, and so you can basically use the DFU tool to basically flash MicroPython to this FPGA. Mm-hmm. So that's.
So then the FPGA will be running a MicroPython environment which you can execute regular MicroPython code on.
On that FPGA. So. So that's if you click on, and I think if you actually scroll, if you just go to FOMU as a CPU.
FOMU as a CPU, is that further down?
Yep.
Oh, there, on the navigation, yes.
So here's a nice picture with the wishbone bus. And so what you can do here is if you go down a little bit further, you can see how it's saying on the wishbone, a little bit further again to there you can see this is using the wishbone tool to write to various addresses to change the LED. Mm-hmm. But if you go down even further, you can actually write RISC-V code. Mm-hmm. You can do a make on it, and then you can just flash that RISC-V code to the using DFU tool. So you can basically start flashing C code on that talks to the peripherals on the wishbone bus. Okay. So I just wanted to quickly go through just in case we run out of time. Mm. And then the next one we go hardware description languages.
we have been going at 1,000,000 miles now so far. So I apologise to everybody that is trying to follow all of this. I'm just barely hanging in there.
Stop getting back to on topic. You are confusing me. So, get back on topic. Yes, okay. All right. I guess what I'm doing is just we've been going through. So Dodge, you've been basically going through this low level of basically starting from the bottom and going up through flashing the device and getting off the ground. My concern was if we keep doing that for another couple of hours. We might never get to some of the more interesting stuff. You might go, is that all there is to it, this low level? And I just wanted to quickly show you where we hopefully may get to if we don't run out of time.
Yeah.
So the other thing you can do is flash.
Let's switch to yours so we can see what you got there. Yeah.
So here you can basically flash the blinking LED Verilog we just showed before. And then finally, this workshop takes you through actually working with LiteX, so basically working with whole CPUs, like RISC-V CPUs, and then using something called Renode, which is a simulation for the whole environment for debugging.
Okay.
So
talking about simulation environments, and you're talking about people using simulators. Is there a big speed penalty for running on a simulator? Like, how does it compare doing this in a simulated environment versus putting it onto the real thing?
I've not used Renode yet because we're working with the raw hardware. My understanding is it's fairly close because these days we've got gigahertz machines, and so you can actually if you basically if your FPGA just doing something simple like running a single processor simulation and using a few hard blocks, that's going to work pretty well. Of course, if you've got it basically trying to take hundreds of inputs and run through the DSPs on board, it's not going to be able to run that very fast, but it's fast enough for just your everyday use.
Yeah, and I think a lot of the power or the benefit of an FPGA is in how it deals with I/O. So doing that within a simulated environment, you're not necessarily going to have the same sources connected. You can simulate some things, but you can't simulate everything necessarily. Yeah. I would think.
It's pretty close apparently.
Okay, great.
Yeah, so sorry for dodging around a bit, dodgy, but I think more was just quickly show that just in case we run out of time to show where we're ultimately trying to go.
Oh, and also it's probably premature, but possible congratulations to Jordan. Jordan said his wife is being induced, so Jordan, you are probably about to be a dad. So if you got, I think Jordan's already left. But anyway, heading to the hospital perhaps. That's
awesome news.
Anyway, I don't have any cigars.
Making more hackers.
Yes.
Very important. Okay, so let's see if we can get Blinky working now. So should we try to do it through your machine?
We can give it a shot.
Okay, let's do that then. Okay, so bring up your terminal again, please.
Okay, so back to my desktop, and I'll move that out of the way. Right. Oops, I'll bring it over the other side so I can still see chat. All right, so
actually, I was going to think one little screw was actually show people where the FOBOOT code is, but maybe just leave that till later. Okay, so you've downloaded the FOMO Workshop?
I've git cloned it.
Great. Okay, so jump into FOMO Workshop. Right, so that work description we just went through the website. The code we're looking at on our screen now is all there. So you can see there's there's light. You can see LiteX is there. MyGen is there.
Just gonna move this out of the way. It's visually confusing. That's better.
Yeah, so if you just do like an ls on the LiteX directory.
LiteX.
Yeah, so you can see it's you can just do more on LiteX workshop.py.
Workshop.py.
Yeah.
Yep.
So that's the Python code that uses LiteX to actually bring up a what's in that? If you just go down another screen. So that's going to build up a whole sock. You can see it says base sock down the middle of the screen. Down a bit further.
Where am I looking for?
Yeah, there, right
there.
there.
Here. Yeah. Sock equals base sock. Okay.
Yeah. So basically working at the Python level to describe a whole system on a chip. So that's the LiteX directory. So if we just go back to the top level again, just ls, and you can see there's a MyGen example and so on, and there's even Rust. You can see there's Rust code. So that's the whole workshop in that. Then you just work through it. So, but let's CD down into it is HDL. So high level description language, and in here there's both Verilog and VHDL examples, and also you can also mix it. So actually mix Verilog and VHDL together, which just strikes me as
really confusing.
Yeah, but let's CD down into Verilog, and there should be a blink and a blink expand. So let's just CD the blink example.
Blink.
Okay. Yeah. So here we are. There's a blink.verilog and a makefile, and that blink.verilog should be the same as what we showed you before, which we just quickly ran through.
Yeah. Okay.
And now there's several types of FOMOs. There's the EVT, which was an early development one. There's the PVT, which was their production one, and there's the hacker one. We've got the hacker version.
Yeah. Okay.
So right, so that's the Verilog code, and you've got
So that's just to take care of the pin allocations.
Yeah, exactly.
Okay.
The pin allocations changed on each of their versions. So got that. So let's have a quick look at the make file. So you can see it uses it needs Verilog, NextPNR, and IcePack. They're the tools out of SymbiFlow we're going to use, and you can just see it there. There's basically just going to go make all. So it says your make file. Now, if we just quit out of that, if you just go ls go up ls2 directories up, and then go to PCF. Oh no, actually maybe it's 3 directories up. Sorry. So
PCF.
Yeah. So if you just do more on like FOMU hacker.pcf.
FOMU hacker.
Yeah. PCF files are just basically definition files for the pins. So basically so to start from the top, you've got your top module, but even your top module has inputs like the clock and other bits and pieces. So it actually gets that information about what clock pin from this file. So you can see on the hacker FOMU, the clock pin is fourth line. There's a pin called F5. So basically, this file says here's where all your pins are. Now, if we go back to the actually, just before we leave that, you can see there's the pins are, you've got your 3 RGB pins, you've got a clock, you've got the SPI for talking to the flash, you've got user pins, those are 4 pins on the outside of the board that we can use, and you've got USB. So basically that's all the pins for the FOMU.
So this, I probably missed this a moment ago. This FOMU-hacker.pcf file is presumably being included as part of the make process. Is that correct?
It is.
So that make file we were just looking at a moment ago, if I scroll back, hopefully.
It's not quite. So there's a small level of indirection. So
Okay.
let's
That's all right. We don't need to chase that squirrel.
No, we can. We're here for squirrels. So we just jump back down into the.
What was it? Verilog.
HDL. Verilog. Blink. Yep. Right. So if you look at the make file, just do more on the make file.
Yep.
You'll see that it includes c.board.make.
Yes,
so if you just,
up the top
so
here.
if you just go colon E,
Yep.
board.make. And then you see in there basically goes what sort of FOMU you've got, and then it loads. Then it's setting parameters for the Yosis command. So it's saying it's an up 5K and it's SG48, which is that's a QFN package.
Okay.
And then also it says the PCF file.
So these flags are then being passed through.
Yep.
And interpreted later on.
Exactly.
Yep.
So basically the board.make file provides the board specific information, and the PCF file provides the pin specific information for each board. Yeah, that's so if we and the other thing down the bottom, you see it's got the environment variable FOMU rev. We will need to specify that.
Yeah. So that's rev for revision.
Yes.
Yes.
The board type. So
rev. Yeah. So that's EBT, etc.
Yeah. So if we quit out of that now.
Yeah.
So you should be able to go FOMU rev, all in upper letters, uppercase letters.
Will it be in my path or
no? FOMU. No, just go. We're setting the environment variable. So FOMU rev.
Oh, okay.
Yep. Sorry.
FOMU
Shell
rev.
Yep, equals hacker.
Yeah. Equals.
Hacker. And then space make.
And then just make.
Yep.
Oops. I supporting no such file or directory. Am I in the right place?
Okay. Gotcha. So we start off by just talking about the OSCAD suite, providing all these tools. As it turns out, we should grab some FOMU specific tools. So sorry about that slight mistake. So what we want to do is I'll just find out where they are. So basically go. I'll get you the path in a sec.
Okay.
I know where I keep reams of notes because this stuff is a lot to keep track of.
Yes.
So export. Where do we get that toolchain from?
Well, while Andy is just checking that out, there are a couple of squirrels that I will chase in the meantime.
Yep.
So as people who've been following me on Twitter know, I've just been trying to do a build of Xeon's vacuum stencil printer project and failed overnight. So the very brief background on that, for those who don't know, if you don't follow Sion, Unexpected Maker, go and follow him on Twitter. So he's doing a project to make a vacuum platform which allows you to put solder paste stencils on and then have them sucked onto the surface of the PCB and held flat so that you don't get any gaps with solder paste going in under the edges. It's a very, very clever idea. And yesterday he finished the design of the fully parameterized version of it so that you can put in some options like what dimensions you want in Fusion 360 and it generates the files which you can then print. I did that and I started printing yesterday and unfortunately, oh look, there's Astra.
Beautiful.
The focus isn't in quite the right place.
High five. High five. Okay, high five. Here we go.
Yes.
Yeah. Okay. Okay. On your mat.
And so I started printing the base plate. The idea is that this is actually meant to be a bit higher with supports on it. And then there is another layer that goes on top with holes and the vacuum attaches on the side so it sucks the air through it. Unfortunately, the thermistor lead on my printer broke overnight, which meant it had thermal runaway on the bed and then the prusa stopped to protect itself, which I am very, very thankful for. So I need to fix my printer and then begin another print. Unfortunately, this is as far as it got. I had said yesterday that I was going to show the progress on the live stream today. I hope to have this ready. I don't. Ah, yes. Okay, Dodgy, yes, that squirrel was just for you. Dodgy wants more squirrels. And, oh, the other squirrel, while...
No, they're working on it.
They're working on it. The other squirrel is... partly thanks to all of my supporters here, I got a new laptop. On Thursday afternoon at 4:40, I ordered one of the new MacBook Pros. I got a 16-inch. It's basically the base model 16-inch, but with the SSD up to 1 terabyte. And it arrived on Friday morning, which I was stunned at. I ordered 4:40 on Thursday. In fact, I think Andy might be grabbing it. Yes, here it is. Oh, okay. It's his now. It's his new laptop.
My precious.
Yes.
So it's a little bit thicker than.
It is. It is surprisingly chunky. Camera is that camera now.
So ports.
Yeah, oh yes, ports. Look at all these ports. It's fantastic.
Ports.
So not only can you charge by USB-C, you can charge by MagSafe. MagSafe is back. We've got a headphone socket, an actual real headphone socket. Turn it around the other side, you've got more USB. It's got it's got an SD card slot in it.
And a real keyboard. A
real keyboard. It's got
It feels so nice.
Yes, and it's got real function keys. It's like... Oh, and 21 hours of battery life on video playback. It's like Apple listened to everything that people have been saying about their laptops for the last few years and just said yes, 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 and did it all. It's fantastic. I haven't really done anything very much with it yet because I've only had it a couple of days. But, Peter said, yeah, but can it run Linux? Well, that's a squirrel we could chase. So, M1, Linux on M1 is on the way.
How much memory do you get for base memory?
16 gig is the base memory.
Yeah, you should get 32. But for me, the big challenge would be the GPU. So it sounds like it's got an awesome GPU, but whether it's supported by the common machine learning tools that we use, because everyone's NVIDIA and CUDA all the way, unfortunately. Yeah. So we'll see how that goes. Yeah, I've got a two teraflop or it's like 2 teraflop. It's like an AMD GPU in my Mac, and I just can't use it with all the stuff I do at work. It's just like what a pain.
Oh, Doug said, and a notch with a frowny face. When I first saw that, I thought, oh no, that's terrible. No. But it's actually fine. I'm in real use because what happens is the notch is in the middle of the menu bar, which is often doesn't have anything there anyway. And when you go into full screen, what it does is put the black bar across the top. So you don't get it intruding onto video content or anything like that. So I thought it would be terrible. It's not a problem. I'm really surprised to say it's not a problem. Yeah. Oh, and as Luke Weston pointed out, a real HDMI port. Yes. It's actually got a physical HDMI port. So HDMI, SD card slot, USB-C on there, like Thunderbolt or whatever it is. 2 more Thunderbolt ports, headphone socket, and it's got the MagSafe charging. And it does, the charge is it's insanely fast. Like it'll do 50, what's the number? 50% charge in some short time, like 20 minutes. I don't know. So, where are we up to?
I was just noodling around on the on my Raspberry Pi whilst you were...
While I was chasing squirrels.
Yes.
So part of the point of that was to say thank you to everybody that supported the fundraising campaign a little while ago, because with the funds that came in from that paid for the Mac Mini, which I use as my main computer, and also got the ATEM Mini Pro, which we're using for doing the streaming right now, and a couple of other things. I also upgraded my microphone system, and there was a little bit of money left over after that. So that went a little bit of the way towards helping on this new laptop as well. So thank you very much for everybody that contributed to that.
Yeah, so I was see if we can get the blinking happening whilst...
Okay. Well, rather than mess around in my environment, how about we do it on your computer?
Yep, sure.
To show the process.
Sure, let's aim for that. Okay, so just working on the right-hand screen, in my FOMU directory, I have I've got FOBoot here. So FOBoot is the directory that you use to create the bootloader that allows us to then have the RISC-V processor with the USB stack and running DFU tool. So what that looks like is there's a hardware section, and so we've got the Python code for that says how do we build up FOBoot, and you can see that in this Python code there's gosh, how am I going to get this quickly? Yeah, it's just a lot of Python. It has like there's some, you can see there's a little bit of combinational logic, which is just stateless logic for doing the clock, and there's things like there's a little bit of reset logic. This is there's a phase lock loop on the this is a phase lock loop on the 48 megahertz clock. And you can see there's these 2 clock domains. There's the 48 megahertz clock and the 12 megahertz clock. So it's just all this Python code for saying how to build. Then there's the base sock, which gives you all the things that hang off the wishbone bus. So you've got your the serial UART, you've got timers, you've got CPU, USB, the LEDs, so a lot of stuff there. There's the memory map for the bus, so it's like
okay.
Right, yeah, so a lot of stuff there. It's all it's basic Python describing a processor. So there's that. That's that bit. Then what's in the RTL? So that's the so this has low level things like there's the RISC-V processor definition in Verilog. There's the LED. Messable is with basically the bus. Yeah, so that's all like Verilog that gets sucked into the Python. And then
so to just pause in there for a moment,
sure.
You said Messable is the bus. Is that like a utility thing that you would use in many different projects in order to provide you that bus? Yeah,
it is. Yeah, just seeing messages. And then the other thing we can also quickly look at is in software. Is if you go into the source code, this is this is the main program that gets compiled to RISC-V, and so you can see at the bottom there's this code that simply says initialize, connect to USB, poll the USB bus, poll for DFU util. So it's just like this is the equivalent of like the Arduino code where you basically got init and set up and loop, just running on the FPGA on the softcore. So basically the Python compiles all the Verilog stuff into a bit stream, and then you have there should be a RISC-V. What is it? It's going to be GCC, something like that. Oh no, GCC. So I've got the tools though. You end up with a RISC-V cross compiler. So you just use a normal GNU cross compiler. Okay. Yeah, so that's what goes on inside FOBoot. Let's just jump out of there. because what we want to do is go into the workshop. So if we go into the
and what I would really like to do is get to I don't want to end this live stream without showing the Rockling.
oh yes, we'll get to that. Okay, so yeah, we're running out of time now because we've only got 25 minutes left. So so from the workshop, let's go into I've got my notes. From workshop, HDL, Verilog, Blink.
Peter said, who knew, this is referring to the M1, that sort of thing, who knew owning your own chip as Cray patents expire would deliver huge performance gains? Just in passing, Andy used to work at Cray, so, and he kind of has one, or parts of one at least.
Okay, so just do a clean, and then we're going to make it for so let's make the bit stream. So it's actually doing this on the Raspberry Pi, so it's not super fast. But this is running Yosis, and it goes through a number of processes of just figuring out how to break the logic down into the cells, and that places them. We can have a look back through this to see if there's anything interesting here. So let's see. There's all these steps, a lot of steps. Run out of history, but you can see it's it's just trying to find cells for all the various parts that are required. So looking for the arithmetic logic unit for the RISC-V processor there. It just goes on and on. But then you get to some useful stuff, which is actually more. I say useful. It's actually more. Right, it's here somewhere. Is it?
Stephen asked, an old round Cray. Yes, is the answer.
It's an XMP22.
Yeah. So.
Yeah, the one you can sit on or sleep on.
Yes. Plus some of the logic boards, I think, that were inside it.
Yep. Which are lots of copper and very heavy. Here we go. This is helpful. This tells you how much of the FPGA we've used. So just to blink and LD, we've used 53 of the 5,000 logic cells,
okay.
the LUTs. We haven't used any RAM. We've used a little bit of the I/O. There's 8 clocks, global clocks. So
okay, we've used one of
those. Yep. We haven't used the phase lock loop or the warm boot. We haven't used I2C or SPI. There's a whole lot of stuff. Oh, it's also got. Hang on, what happened there? I must have actually done a paste.
Yeah.
Sorry about that. It also has I3C implementation. Who knew? But you can see that whilst we didn't use the LED pulsing breathing part, we have used the LED driver. So we've basically used bugger all of this of this chip. Anyway, so anyway, then it goes and places everything, and then we're done. So now what we should have is a blink.dfu file, and so we can now just go. Now I'm going to show you what happens on the console. So when we flash it, you can see it's flashing to the FPGA.
See the progress, yeah.
Right. So that now worked.
Oh, well, that's confusing. Error. No error condition is present.
What's happened there is because that bit of error, all this. Its FPGA went from running a RISC-V processor with a C stack and USB and DFU, downloading stuff. And as soon as it's downloaded, it's immediately then gone and done a warm boot, and it's now running new. That basically took our bit stream and got to the flash memory.
Yep.
And then we did a warm boot, where it now loads from the flash memory this new bit of Verilog, which is basically all it does is blinks a LED. So basically, it's dropped off the USB bus.
Okay. So now, in order to get new code back onto it, maybe I'm jumping ahead too much.
No, you can talk about that. Okay, so let's look at this on the downward camera.
Yep.
Yeah. So we can see it's blinking. This is its normal sort of like a greenish color, and then when now I'm going to hit return to flash it. So I'm flashing now, and now it's changed to a blue
quickly.
And then when it's completing flashing, it is now not flashing at all. So I've broken it. Now why has that happened? Probably because I've set this up to work for the Rockling. I think is what's happened. Actually, no, I'm running it. This is a test. I was trying to drive the audio codec. So let me just go back to the normal blink code. -s blink .original. Sorry, blink v .original. I'm just what have I done?
There's an extra dot in there, I think.
Oh, I'm leaning on the keyboard. Strange. Sorry.
Andy is trying to work with his laptop and everything at a bit of a strange angle.
Yeah.
It's a bit hard to tell on camera, but we're really jammed in here trying to get everything in where you can see it.
Okay, so I'm just resynthesizing the bit stream now. So that's just going through that resynthesis.
Okay, so that is doing what we just saw before, but it's doing it with the different code.
Let's see.
So now we'll switch back to the overhead.
Oh, okay, so here we go. So I'll just unplug and replug it.
Okay.
Okay, so it's now just running. So whenever your power cycle goes back to running the RISC-V stack.
Okay.
Basically on the flash memory, this FPGA allows you to have allows to basically warm boot the FPGA and reload from a different part of the flash memory.
Mm-hmm.
And so there's slots on the flash memory where the slot 0 effectively is the faux boot and the whole RISC-V stack.
Yep.
And then when we do use DFU tool, what we're doing is we're flashing into the second slot a new bit of Verilog.
Okay.
So
So when it does the warm reboot, it then loads from the second chunk
Slot,
of memory, the second slot, and then in what situation does it, if you then power cycle, does it always go back to the first one, or can it go back to the second
in
one?
its current configuration, yes, it'll
Okay.
it'll always power cycling or resetting the FPGA because it's literally hitting the reset pin.
Yep.
Causes it to load back from slot 0 again.
Yep.
So
So
it's-
as long as you have something sensible in slot 0, you can leave that there, and then you can play around with your own things in slot 1.
Exactly, and so it seems to be fairly robust. Like I haven't bricked one.
Okay.
So basically, once we've got faux boot onto the FPGA into the flash memory in slot 0, you can just continue to use USB to flash and reflash fairly safely.
Okay.
It's
And the worst case scenario, even if you did nuke slot 0, you could use that SPI technique to
just reflash
put it back in
exactly,
again.
yeah. And it is possible to nuke it because from the FPGA you can write to any part of the flash memory.
Okay.
So as long as you're not
so
writing
it could self-destruct.
Yeah. Yes. But anyway, so let's see if this worked. So I'm just reflashing it. So it's flashing light blue, reflashing the FPGA, and still
And
screwed up. What have I done?
We have to have a demo fail. It's the rule.
Let me see what I've done wrong here. VI link.v.
So we've got, what was it set
Actually,
to?
I'm just going to check and make sure I've actually got the right FOMO one here. 'Cause,
Okay.
I could have accidentally picked up your one by mistake.
Oh, okay.
It says it's a PVT.
PVT.
That's weird.
Okay. So can you change that in the
Yeah.
config and
I could.
reboot?
I'm a bit surprised by that.
Curious that it's reporting itself as a PVT.
I wouldn't. That's why I'm thinking. I just grabbed the one off my desk at home, and that could be your original PVT. So
it could be.
actually, let me actually. So in fact, I think it might be what I'm going to do is I'm going to grab. Yeah. So pull this out of the. I think this. Whoop, just dropped.
So
Do not need it.
just a little bit of explanation here. The EVT, PVT, and the hacker versions, what we're talking about here are different hardware revisions of the FOMU, which is this little board that Andy, you can see here in the USB connector. And so it went through several generations, and they have slightly different hardware setup. So when this this code is being prepared for it, it needs to know what its target is.
And I grabbed the one that we were just using because it's the LED was easier to see. So you can see the LED is not so easy to see on this one. And I think that's how actually. So if I actually go DFU util-L now, see it says FOMU hacker.
Yeah, I'll just switch back to that. So here we've got the DFU util,
So-
and previously it was
So the previous one I was using was the PVT,
yep,
and now we've got the hacker one.
the hacker version.
Now, would you believe I've got like 50 hackers and like
picked up the one PVT.
Yeah. All right. So now if I just reflash that with hacker, and now if I flash it,
Yep, and I will switch back to overhead camera so we can see the result. You can just barely see that it's breathing blue,
light blue.
and now it's,
There we go.
Yes, that's better.
And then you basically got red, green, and blue LEDs on there, and based on the counter, that 28-bit counter, the 48 megahertz clock just cycling through it.
All the way back to the start of what we were looking at.
Yep. So we've got 15 or so minutes. Hey, look, we've been very quiet today.
It's been very good.
Yeah, let's talk about the Rockling.
Yeah, let's talk about the Rockling. Okay, so While Andy's grabbing some things out,
Well,
where...
you can just show this.
Oh, I can show that.
Yeah,
Okay.
That's a new.
I'll just wave this at the screen for a moment. There's going to be some more explanation soon. So I was talking right at the start of this about the Open Hardware Miniconf, and the project that we are working on for the upcoming Open Hardware Miniconf is an extension of the conference badge project from last year. So the conference badge last year, I have one just here that I can drag across. This is the 2020 LCA 2021 conference badge, and it's got a couple of screens on it. It's a little bit out of focus, unfortunately. There is an ESP32 on here, and it has these add-on headers which allow you to put on extra boards. So this is a little board that looks like a tux. This was designed by Andrew, who may be in the chat here today. I'm not sure, I haven't seen him pop up. Pancake Legend, if you're there, that was his design. There's a little prototyping add-on. So this was the conference badge, which is basically an ESP32 running, we had it running MicroPython with some displays and inputs and things and touch sliders. So the evolution of that design was to take the little tux add-on that Andrew did last year and scale it way up. So it would be really much easier if I got this off, wouldn't it? I'm going to get these off so that you can see what I'm actually trying to show you. One off. I'm going to show the blank PCB first. So this is the little add-on from last year, and then it got scaled up to its big brother right there. So what we did was promote the add-on. So the badge with its add-on, the add-on has got scaled up. So the new badge is the crystal tux shape. You can see it's got headers here for putting add-ons, so we could have a tux add-on on a tux, as you can see right there that Andy's got. There is going to be a screen across here, and it's got touch sliders once again, ESP32. Now, this is the base badge, but on top of this, there is an add-on, and this is where the FPGA part of it comes in. The base badge functionally is going to be almost the same as last year. ESP32 running MicroPython, and there is one just here. So this is one with, I'm just going to take this off first. Okay. And this is not the final screen. This was a screen that was patched on for testing because we didn't have the real screens yet, but there will be a smaller screen across the front here where Tux's eyes are. So we'll be able to display his face or information or whatever we want to on there. And then this is the FPGA Magic. So this is the Rockling, which way up, I don't think it matters which way up it goes. No, that way. So the Rockling is an FPGA board, which is an add-on for the conference badge, and it has a front end on it for, this is the magic bit,
the theremin.
For the theremin. So what we've got, and this is still being developed, it's not entirely hardware validated yet, but it's pretty close. The idea is that you can have an input for a theremin so that you can use the FPGA for processing the input from the sensors. So as you move your hand in space near it, the FPGA can be reading the input from the theremin front end, which is implemented in hardware on here. And then that can be used for controlling audio output so that you can play music essentially by waving your hand around near the badge. That's the goal. So this is designed to go onto the conference badge. So now we have Tux holding the fish, which is the Rockling, which is the FPGA based theremin. And you can see here there is a USB hanging off it. That wouldn't normally be attached while this is in operation, but maybe you can explain a little bit more about what's actually on this board, Andy.
Sure. Well, if you switch to the camera view, if you don't mind.
Yep.
Okay. So, Tim's work with the FOMU, like the workshop and everything, it's just fantastic. But personally, I was ultimately frustrated because the FOMU doesn't have a lot of I/O in it, and so what I did was I took one of the FOMUs, which is that's the FOMU that's there.
Under that blob.
Yeah. I put a I think it's a reset switch on it, so it just makes it easy to reset. And then I basically connected 4 wires plus power and ground to basically onto a breadboard, so I can start breaking out the I/O and doing things with it. So you go, 4 I/Os. There's not much you can do with that. Well, but at least it's a little bit of a start. But you can actually, if you've got I2C or SPI, you could then talk to I2C devices. So it just requires your imagination to to work with it. But
and mechanically it's very difficult though, because it's very small wires soldered onto tiny test points.
Yeah. So all props to Tim and his team for producing an awesome launching pad, but to have to 3D print your own flash and get off the ground device with programs to get off the ground, that's a big impediment. To have to do this sort of stuff to actually expand out the I/O is also a bit of an impediment. And I think an important question people always ask is, well, why FPGA? What do I do with it? And so what we want to do with the Rockling is try to provide an answer to that. And so some shout outs. Obviously.
Oh yes, Tim, many shout outs.
Obviously Tim, Sean Cross, and their whole team about doing the whole FOMO stuff. Just awesome. And Tim's been very supportive. Bob Powers, who's on our HMC team, he designed all the hardware. So Andrew has done things like these Rocklings. They actually tile the plane. So basically, if you have a couple of Rocklings, they actually fit together, and you can actually tile a plane with the Rocklings. They fit perfectly. That's not that Andrew's obsessive at all.
Not at all.
There's a backlit LED that fits there, and it basically shines through the eye, which has got some nice sort of circuitry. So that's got a nice touch. And so Andy, my good friend Andy Kitchen, came up with the name and the some of the driving thoughts behind the project, like the theremin. Bob Powers it's probably the most complex 4-layer board project we've done for the HMC. So basically, let's put some stuff on here.
It is quite a tight board.
Yeah, but it just looks beautiful. So basically, in the middle you've got the FPGA. And then there's the flash memory sort of sitting somewhere there as well. So it's got the flash memory. Then there's a DAC. So from the FPGA to the DAC, that allows us to bias the circuit for the volume and the pitch.
So the DAC is digital to analog converter, and what that allows the FPGA to do is generate an analog signal essentially.
And so we've taken the Open Theremin project logic, and that then goes back into the FPGA using 2 pins. So that's the theremin part. Oh,
and for those of you who don't know, the 30-second background, a theremin is a musical instrument which works by detecting varying capacitance, which is based on detecting the position of your body. So they typically have 2 antennas. You can consider them antennas at right angles, and by placing your hand into the space near them and moving it, you can change the sound that is coming out of the instrument. So it's a little bit like a synthesizer, but the input to it is the human body. So if anyone is interested in that, and it creates really spooky sort of electronic sounds. If anyone is interested, go and check out the theremin. It's pretty interesting.
Okay, so the other parts on the Rockling. So basically, we've got a theremin input here. So it's a musical instrument. We've got an audio codec that you talk to over I2C and I2S. So that allows you to take stereo from. It really goes actually to really. Basically, you can have stereo from a mic or out to headphones, and also we've got an amp to go out to speakers, so it does all that switching. So you can sample signals on I2S, so that would be from the FPGA. You can also does things like stereo base equal. It's got an equalizer, and it's basically everything you need to put an MP3 player to basically do audio. So it's very very powerful. So now this FPGA also has 8 DSPs, and so we want to I guess and also we have I'll also say there's the SAO, which basically is I2C power ground and two GPIOs. So
the SAO is what I was referring to earlier as the add-on. I didn't use that name, but that's the simple add-on that goes onto the conference badge.
So all these little things, they're just examples of little SAOs. And so our Rockling is basically a really complex SAO. So you basically, from the swag badge, which provides us our user interface, there's the screen and the touch sliders, you can basically over I2C talk to the FPGA over I2C bus 0, and there's another I2C bus 1, which allows the FPGA to talk to its internal peripherals. So FPGA's got 2 I2C buses and an SPI bus, and also I2S for the audio. So there's a lot going on here. But hopefully hopefully by making an audio project, so it's audio processor that's used for doing audio in general. We've got the 8 DSPs on the FPGA, so we can hopefully do some cool synthesis and processing. It could be a synthesizer in its own right. Yes. And then we've got the theremin input just to make it into a musical instrument.
To make it fun.
Yeah. So that's what's going on there. So let me get that out of the way.
So what we've got here with the Rockling is a specific. It's an FPGA dev board, but with some interesting peripherals attached to it that allow you to really explore some of the things that an FPGA can do around things like signal processing.
So now, if I bring the Raspberry Pi into play, there we go. So that Rockling is running faux boot now. So it's just like the FOMU before it. It's running that. So let's see what I can do here. So my Raspberry Pi, what have I got? So if we go to tool play, how are we going for time? Oh,
a few minutes.
We might actually sneak something in here. So FOMU, let's see, so FOMU. Right, I'm going to try and, okay, here you go, Andy's Rockling, Andy K's Rockling DFU. Ooh, could I get all that? October 23. Okay, let's go for it.
Okay.
Right.
Go for broke.
Go for broke. All right. Right, so we're going to do a CD play FPGA FOMU. So finish the shout out. So
yes.
So Bob Powers and Andrew Nielsen have done pretty much like the hardware design and getting that board produced.
Yep.
And my friend Andy Kitchen, he's basically done all the heavy lifting on the FPGA side, and so basically getting it up so it can run a RISC-V processor with a wishbone bus. He's got the I2C stuff going, a lot of bits and pieces going there. So that's a bit we're about to show now. So if I go
actually on the subject of shout outs.
Yep.
The name Rockling, which I think Andy Kitchen came up with.
Yep, he did.
Which is an homage to a musician, and I can't remember her name.
Clara Rockman.
Clara Rockman, yes. So one of the reasons that the theremin became so famous is that the original inventor of the theremin teamed up with Clara Rockman, and she became very, very skilled at using it in performance. And so it was really her use of it that popularized it, and so the name of the thing that you see on the screen there, the fish, called the Rockling, is a tribute to Clara Rockman.
Okay. Gosh, I got to remember how to do all this. Okay, so I'm on this extra grep Rockling. Right.
We got countdowns on the screen for how many minutes we got left.
Come on.
3, 2, 1.
Nice. Is it lunchtime?
Here we go. It almost is.
I bought lunch. Here we go. Astra's going to share lunch with you, John. So
okay,
we have
dog treats.
We have lunch. Here we go, John.
Thank you.
Yeah, gross. So let's see if we can compile the code. Right.
Oh, Aaron just asked a very interesting question.
What's that?
How power hungry is the FPGA you're using there? That is a very good point.
Well, it's intended to be very low power. I haven't actually measured it, but it's the FPGA that was used in as mentioned before in the iPhone 7. So but basically, it's going to come down to what it's doing. So if you've basically got all the DSPs hammering away and stuff like that, it's going to be using power. But if basically you've got it just really just checking I/O pins, it could be very low power.
Okay. that's interesting to know. That's a very good point, Aaron. Thanks.
Yeah, you've got these two ends of the spectrum. You can use them for very low applications where you can just only have just the small amount of logic you want being clocked. Because with CMOS, you're only using power when you change when the gate changes. Yeah, so you can slow the clock down, you can stop the clock, whatever.
Yeah, with CMOS logic, you used to be able to actually pause the computer by just stopping the clock.
Yep. And the other end, which is interesting, is for things like so the other thing is this machine. This FPGA, there's examples for using doing wake words, and you can run small neural network applications on them for doing either wake words or small image processing for your like if you had an Arduino or an ESP32, it doesn't have enough horsepower to do image processing.
Yeah.
You can have the FPGA do that. The other end of the spectrum, like the top end FPGAs, a Xilinx one, which I think it's like 12,000, nearly 13,000 DSPs running at 500 megahertz. That's running to nearly 40 terops, which puts it in the same class as an NVIDIA T4 GPU. So my guess is that it would appear that Xilinx are going to go try and eat some of NVIDIA's lunch.
Okay.
Yeah. And DSD is that Defence Signals or something else?
Yeah, when I see DSD, I think Defence Signals Directorate. I'm not sure what you're referring to there, Dodgy. So Andy was just talking about wake words as audio processing. Peter, okay. Peter says bye. I think what he's doing is trying to get us to say goodbye.
No,
not yet.
Okay.
Yeah, and there is a microphone input on this.
If you go back to the screen.
So we'll go back to here. We are pretty much out of time now, but wrong one. We want that one. But we'll finish this a bit off.
All right. So keep chatting. I'll keep working.
Yeah.
I'll keep working
Okay.
here while you're. So,
Yeah. So part of the objective with this whole thing, with the Rockling project, is to create an FPGA-based dev board that can now that you can use for different purposes and experiment with things like audio processing. So it has a socket on it that allows you to have a microphone input, and is it microphone input? I can't even remember.
Yeah,
We've got
microphone.
so it's microphone input as well as the headphone output. So the Rockling badge, by running the appropriate code on the FPGA, could be used, for example, to do voice control. You could have a wake word detection circuit on it, or wake word detection code, and take the input from the microphone input. So it's kind of whimsical in its shape, the fact that it looks like a fish and it's an add-on that goes onto a conference badge, but it does have its own onboard USB, and as Andy has shown, we can connect to it via USB. I'll switch back to here, and you can use it as a dev board in its own right. You don't necessarily need to use it by plugging it into a conference badge. So yeah, I'm really excited about it. I think this is a really cool board to play with, and I'm just starting to learn about FPGA, so it's a very quick orientation for me getting my head around all of this sort of stuff. So many layers to this. Okay, are you switching over to the other laptop?
Yeah,
rather than using the Raspberry Pi?
Yep, that's the goal.
Yeah.
So hopefully I didn't lose the connection. I did. Let's see. So,
because the laptop was asleep.
It went to sleep because I.
Oh, did it come back?
Oh, actually. Oh,
it's back on the network.
Magic. Okay.
So we'll switch back to your desktop.
Okay. Yeah. So.
All right.
So what I've been able to do is just using this command here, rockling.py. That's Python that uses LaTeX and MyGen to create a sock. So it gives us the wishbone bus, and also this with analyzer that basically puts there's a project called Lightscope, and it basically puts a small signal analyzer, if you like, capture inside the FPGA. So you basically can say, I want for these pins or signals, I want to basically capture those and then dump them back over USB. So you basically run like a small, it's like having a digital oscilloscope inside your FPGA.
Building it, inside your project.
So now that should hopefully, if I'm in build, I think it's build, Rockling, and it's saying it's like gateware. Where's the DFU file? So maybe this, I think it's there somewhere. So if I just do history grep DFU. So just grep DFU. Oh, here it is. So there's the command for flashing. So let's see if our Rockling is there. Yep, there's our Rockling.
Okay.
So you can see, so it's by using the FOAMU EFT bootloader. Now let's flash the code there. So you can see it.
You want the overhead view?
Yeah. So is it being 1730? So you can see, I'm about to flash it. So you can see the eyeballs glowing green.
Yes.
Now when we flash it, you can see it's now gone to light blue.
Yep.
We're downloading, and now it's gone. The eyeball's gone off.
Yes.
Now, when I first saw this before chatting to Andy, I thought I'd broken. It was broken, but it's not. It's just not displaying any signs of life.
Okay.
But we've now got the wishbone tool. So if I go history grep wishbone, let's see. I've got a CD. Have I got wishbone here? No. Okay, CD2 play, CD play, FPGA, FOAMU, HMC.
So, Luke clarified, DSD in this context is direct stream digital audio format.
Okay.
And also, Dodgy asked, does this have any advantages for voice recognition over conventional methods? Well, I cannot authoritatively answer that, but my understanding is that doing voice recognition and wake word detection traditionally is very processor intensive. So doing it on something like a microcontroller it's working fairly hard to do it. Whereas doing this on an FPGA, it can be running at I think a lower power level, and you can use it for, so the idea with wake word detection with things like voice recognition systems is you don't want them listening all the time, because it's using, well, there are many reasons, including privacy, etc. So what you want is something that will trigger it, and from that point on, it will begin processing the sound that it hears. So when, this is a whole other rabbit that, or a squirrel that we won't chase right now, but the design of voice assistants involves a couple of different stages. They are not listening constantly for everything that is said. They are typically, when they're in a quiescent mode, they are listening for a wake word, and that is the only thing they are listening for. And once they hear that wake word, they then go into a different mode where they start processing the incoming audio and trying to analyze it. But to be analyzing all the audio that was coming in all the time would normally require pushing that up to a cloud service, so it uses up lots of bandwidth. Whereas the wake word detection can be done locally in a very small optimized way, so it doesn't need an external connection to detect the wake word. And then once the wake word has triggered it to go into its live mode, it then starts sending the data off to a cloud service for the full voice processing.
Okay, if we go back to the, okay, so what I can show you now is, if you go back to the screen very quickly.
Yep.
So, I can run if you like, this wishbone command. So I just basically just do it here like that. That's basically saying to the address hexadecimal 2000, write 0x AC, which is a command to reboot, basically causes the device to reboot.
Okay.
So basically, if I go, let's see, if I go diff usual -L, we'll see that the device isn't currently on the isn't available to DFU, but if I now go and reboot it, hopefully, see if that works. No, that didn't work. Oh, okay. But I'll just power cycle it.
Okay.
So power cycle. So if we go back to the top-down screen.
Oops. Overhead. Yep.
Yep. So now if I reflash it again. So I'm just flashing it now. So it's gone light blue, and then the light's gone off. Now what I'm going to do is I'm going to send wishbone commands to basically talk I2C talk to the LED. So that's so if we go back to the main screen, what that looks like is tools LED on the right hand side. On the the wishbone tool is basically looking at this file called CSV. That file basically shows you all the addresses. So if we look at what RGB control register is, that's RGB control is probably down here a bit further. Okay, RGB control is the address 3808. So if we write 07, if we write these sequences of if we poke memory at these various addresses and using these values, we're basically talking over the wishbone bus to the LED peripheral and controlling the LED.
So just to recap what Andy explained right near the start, the wishbone bus ties together the various elements within the FPGA, and in this case it's also being exposed to the computer externally, so that from the computer we can interact with the devices that are on the bus within the FPGA.
Yep. And so this what we are using this for right now is to be able to send commands to the using Wishbone to the I2C bus to actually start exercising the audio codec and then the DAC and so on. So we can actually start to just really basically from our laptop, which is much more convenient, drive those devices to make sure they've got the addresses and commands right, the hardware's working. So we're doing that at the moment. And then after that, what you can then do is you can just start writing C code on the RISC processor, then just exercise devices on using the FPGA itself.
Yeah, so it's a way of bootstrapping and testing that things are working in a manual way before you implement it all internally.
Exactly. And I don't know if it's going to work. So the final thing might show before we finally just stop for the day. Control T. I go to to play FPGA source access environment, and then
Iggy says, and I think I spent all that money on that Xilinx course. So I don't think we're equivalent to a Xilinx course. But thanks, Iggy.
Let's see. So if I get there it is scp dump.vcd to eg@nomad.local. Dump. This is the fun of working across so many machines. So yes. If I go GTK K-Wave dump, it's going to work. Yes.
Okay. So this is the analyzer.
Yep.
Hang on, I'm just going to move this out of the way up here.
So what's happened there is I'll just get a bit of paper. Where's the pen's gone? Not time for a different colour pen. Time for a different colour pen.
I'm going to stick us down there, and we'll switch back to overhead.
Yep. So firstly, you've got the FPGA. My brain's basically we've got the bus, and off they've got various blocks like the LEDs, I2C, and so on, and then that goes across to our laptop. So we've got the wishbone command is on our laptop.
Yeah.
What we've done is we've put this thing called Lightscope, which is this little analyzer. It's just another block, and what it can do is it can basically look at any of the other signals you want. Basically, all these signals come to Lightscope. It has a little buffer in RAM, and what it does is periodically with wishbone commands, you basically get that dumped. Basically, do a dump across the over USB back to your laptop.
Yep.
And it all ends up in a file called dump.vcd. And this is a format that a program called GTK Wave can basically interpret.
Okay.
So
this is similar to using a USB-based logic analyzer, where you have the software that runs on your computer. It talks over USB to the logic analyzer, which connects to the specific signals you want to talk to, except that in this case, there is no logic analyzer. It is within the FPGA. So it's been created as a soft block.
And so what Andy was doing here was from the Thurman input you have input stage. You basically have a volume and pitch, and they get what goes on in the antenna basically gets transformed into signals roughly around 500 kilohertz. And as you move your hand closer and further away from the antennas, those signals vary. And so one of the logic blocks we've got inside here is a frequency counter, and what we're looking at here is frequency count 0. Yeah, hang on, do I slightly do that? There we go. We're basically looking at the input signals of those two theremin inputs. So and we can see it. Unfortunately, it's not looking it's not looking good at the moment. That's the bit we're diagnosing.
Yeah.
But hopefully by the end of so what we'd do is we'd get a physical digital oscilloscope. And we basically probe the board with the physical oscilloscope to basically see what the circuit is looking like from outside the FPGA. And then we look at light scope to basically see what's going on inside the FPGA to diagnose the logic there.
Yes, so you can correlate those two. I'll trace the signal path through.
So hopefully what we've conveyed is that this is a fairly complex world, but once you've been playing around for a while, you basically get down to these simple to use tools now for basically taking Verilog or Python code, or in fact a whole SOC code, turning that into a bit stream that can load onto the FPGA very easily. You can have soft CPUs in there. You can be writing C code in the FPGA. But the steps you got to do is first validate the hardware, and you can basically once you so our first problem we had was we couldn't even get the clock on the FPGA working correctly because we'd chosen the wrong pin. So that was like everything's just dead. Yeah. And we got the clock up. Then there was issues trying to get the USB up, but then that was just cold solder joints. But we got the USB up, and once we got the USB up, we could then start. Well, we were able to flash the flash memory using SPI. So we got that up, so we could see some lights, the LED blinking. So fantastic. Yes. But then once we got the USB up, we could basically with Fogo, we could then start just using USB to load the FPGA up, which is more convenient again. And then once we got the wishbone bus up, we could then start talking to individual peripherals from the laptop. And as we get to each stage, your ability to diagnose becomes
much easier. You can see what's going on. Yes.
And then the last thing is by putting light scope in there, basically gives us like an oscilloscope inside the FPGA. Yeah. And then once you've sort of got the blocks working inside your FPGA, and it's got a RISC processor on there, you don't have to be working Verilog all the time. You can be working in C code, basically just using libraries talking to I2C. So it was anyway, that's where we're trying to get to.
Cool. Notifications. At least some of those notifications, I think, were Peter saying go to lunch.
All right. All right. Hopefully,
I think that seems like a reasonable place to wrap it up today. Yep. So we've got through a lot. A huge thank you to Andy for coming along and giving me this crash course in FPGAs, because I'm kind of learning along the way, and you can watch over my shoulder as I flounder around and figure it out. So, any last minute questions, things that people want to say? Gerald, thanks. Yes. 10K pull-ups. There was a question there. This is off topic, but there was a question about the MCP 23017. And which is an I2C based I/O expander, and it's already been answered. 10K pull-ups. That particular chip does have internal pull-ups. You can enable them through software, but they are weak pull-ups. I think from memory they are in the order of 100K, maybe 120K, which is quite weak, and potentially there could be noise that could cause those to give you spurious inputs. So on my very early light switch input boards, I was relying on the internal pull-ups. I actually never had any problems with them, even with long wires connected. But my current versions of the light switch controller boards have 10K pull-ups on them, so that it is fairly strongly asserted in hardware external to the chip. Okay, so Xeon, yes, it was pretty full on. I've got to fix my printer and get back to doing the version of Xeon's thing maybe later tonight. But can it analyze itself? Okay. I've got to the rambling point where I don't even know what I'm saying anymore.
Definitely lunchtime.
Yes, Chip. Longflare, which is Chip, says this particular chip is depleted, and so are we. So it is time to give Astra some doggy snacks and to give us some human snacks, and for you to go and get lunch or go to sleep or have dinner or whatever it is in your part of the world.
Other thing mentioned is the hackerspace is having a sausage sizzle at Bunnings Hawthorne. So
yes.
yep, so satisfy your Bunnings urges to and grab a sausage, support the space, and the hackerspace is open again, which is great. So,
yeah. Okay. So thanks everyone. I think I need a little bit of a nap after loading my brain up with all of this stuff. So I will catch you all really soon, and stay safe, stay happy, and I'll talk to you later. Oh, and go and build something awesome.
Here we go.